Good morning, everyone. This is Akshat Pandey, a BTech second year student enrolled in Computer Science Engineering at Manipal University, Jaipur. I'm going to present my case study on the IBM Power Architecture for Computer Organization and Architecture. In this talk, I will cover the design overview, key features, instruction set, and performance techniques of the IBM Power family, and end with a small assembly simulation demo. Here I begin with the outline. Here what I will cover is an introduction to the architecture, its instruction set, data path and pipeline, memory hierarchy, and some specialized features like multi-threading and AI acceleration. I will share its historical importance followed by a short simulation demo and conclusion. Let's go through the architecture overview. The IBM Power Architecture is a RISC design developed by IBM in the late 1980s. It was built for high performance and scalability, mainly used in servers, supercomputers, and AI systems. It follows a load store model, uses fixed 32-bit instructions, and support high-level parallelism, meaning it can execute several instructions at once efficiently. If we talk about instruction set architecture, the ISA defines how the processor executes instruction. Power uses fixed 32-bit instructions and support immediate register and displacement addressing. For example, adding R3 R4 10, that will do adds 10 to the value in R3 and store it in R3. That will add the value of 10 to the value in R4 and will store it in R3. It also has powerful branch and link instructions for function calls and condition registers for parallel flag checking and improved performance. If we talk about data path and pipelining, the Power architecture uses a 5-stage pipeline: fetch, decode, execute, memory, and write back. It supports superscale and out-of-order execution, which allows multiple instructions to run at once without waiting for the others to finish. With branch prediction, it avoids pipeline delays and keep the CPU running efficiently. If we discuss about memory hierarchy, IBM Power processors uses a 3-level cache system, split L1 caches for data and instruction, a unified L2 cache, and a shared L3 cache. Features like prefetching and speculative loads help access data faster, and high bandwidth memory controllers support heavy workloads like AI and cloud computing. If we discuss about the specialized features and parallelism, power chips are known for multi-core and simultaneous multi-threading or SMT, where each core runs multiple threads. They also include SIMD instructions known as anti-vec or VMX for vectorized operation. Power processor support virtualization through logical partitions and now integrate AI acceleration in newer versions like Power 10. Now if we discuss about the historical significance and comparison, IBM Power processors have powered many enterprise systems and even the PlayStation 3's cell processor. Compared to ARM, both are RISC-based, but ARM targets low-power devices, while Power focuses on high-performance enterprise and computing. Recent versions like Power 9 and Power 10 are optimized for AI data analytics and cloud environment. Now moving on to the simulation part, here I have demonstrated the computation of 8 factorial using IBM Power assembly language. For this, I used the QEMU Power PC emulator, which allows us to simulate IBM's Power architecture environment on a normal machine. The OS which I have used for this demonstration is the popular Linux platform Ubuntu. So let me briefly explain how the code works. So for the proper functioning of this code, I have to create 2 files. The first one is the factorial.s and the second one is the main.c. Now I am going to explain you how these files are important for the execution of this code. So let's first discuss about the main.c. In my C program named main.c, I declare the factorial function int factorial bracket int n. The line simply tells the compiler that the function is written externally in assembly. Then, inside the main function, I initialize n as 8. Next, I call the factorial function n as an parameter which transfers the control to the assembly routine. Finally, the result is printed back in C as factorial of 8 is 40320. So the C file mainly acts as a bridge to call the assembly function and display its result. Now if we put light on the factorial logic like this file factorial.s, which refers to the assembly language, then if we look carefully at the core logic inside the file factorial.s written in IBM Power Assembly, it starts with .text and .global factorial. This defines the text segment and makes the factorial label globally accessible. The first instruction, that is this one, CMP WI R3, 1, compares the value in register R3 with 1. If n is less than or equal to 1, the instruction BLE base case branches to the base case. This handles the factorial base condition returning 1. If we see the recursive frame, next we create the stack frame using STW R1, minus 16 bracket R1, which allocates space on the stack. Then we store the link register and the current value of n. That's done by this function mflr r0, followed by stw r0, 20 bracket r1 and stw r3, 8 r1. After saving, we decrement n by 1, addi r3, r3, minus 1, and then recursively call the factorial function again with bl factorial, meaning branch and link to factorial, which calls the same function again. If we look at the multiplication step, after the recursive call returns, the next few lines handles the multiplication. We load the original n from the stack using this function lwz r4, 8 bracket r1, and then multiply it with the return result stored in the r3 using this function mullw r3, r4, r3. This effectively computes n multiples by factorial of n minus 1. Now the next step is the stack and return. Finally, the program restores the link register and the stack using this command lwz r0, 20 bracket r1 and mltr r0, and finally addi r1, r1, 16. The instruction, which is this blr, then returns from the function passing the final value in register r3 back to the C program. If we look at the base case, which is mentioned here, the label base case defines the stopping condition. This li r3, 1 simply loads the immediate value 1 into r3, and then this blr returns effectively returning 1 when n equals to 1. Now let's look at the execution part of this code. So this is the execution part. Here to compile and run this, I first use this command, the above mentioned, this PowerPC to this MREG NAMES. This compiles both the C and the assembly file into a PowerPC executable. Then what I did is I executed it inside the QEMU using this following command QEMU-ppc./fact_ppc. The output of the terminal here shows the factorial of 8 is 40320, which verifies that our assembly logic executed successfully inside the IBM Power Architecture Simulator. So this simulator practically demonstrated how the IBM Power instruction set, stack handling, and the recursive call works together efficiently at the low level. It connects our theoretical understanding of RISC architecture with a real working assembly example. Now, to conclude through this case study, we have explored how IBM's power architecture represents the power of RISC, which is also known as RISC design, combining simplicity with massive parallel performance. We have seen how its instruction set, pipeline efficiency, memory hierarchy, and multi-threading features make it ideal for today's high-demand applications. And finally, by simulating an assembly program, we got hands-on insight into how real operations flow through this architecture. Thank you for your listening, and I hope this helped you understand why IBM Power continues to be a key player in the modern computing. Thank you for your patience listening, and have a wonderful day ahead.